Okay, have we got a full house? I think we've got a full house, roughly speaking. Apologies, just turn my phone off. We're probably going to be interrupted very soon by some fire alarms going repeatedly and annoyingly for about 5 minutes. Don't worry about it, okay, it's just a practice. They practice the alarms repeatedly and annoyingly every Thursday morning at about 8:45. Right, so you'll have a break. You can start shouting abuse, whatever you like, during that time. Okay, so we're going to have a look at polymer crystallization today and a couple of other things briefly before embarking on two lab sessions, one on X-ray. Oh yeah, do you know that? That's not it. You think that's it, but it's not. I'll do another 6, 7 times. All right. Right, okay. So before doing lab sessions on thermal analysis and some X-ray scattering, okay. The thermal analysis is all about crystallinity and thermal transitions, and the X-ray is about structural analysis. You know, it's all very well saying we get crystals, but what are they? We don't know what they are. We can't pick that up from simple thermal techniques. Anyway, we'll take a little drive through that now. How many more, Michael? Two more. Okay. Michael keeps an eye on these things. He's got a log that he writes down every week just to make sure. Okay, so the first 2 slides are pretty much the same as they were yesterday, actually, when I was speaking about whatever I was speaking about. That all processes, all manufacture processes for polymers and for, you can argue to a certain extent for metals, operate on the same principles of heat, flow and cool, okay? Somewhere in there is the forming process. And by understanding these thermal and rheological properties, we can start to understand the process, and also we can start to, hopefully, be able to fix the final product properties, okay? Okay, so just looking at this image again, so we're looking at a different side of this than we were yesterday when I was talking about rheology, where we focused pretty much on this process, on this flow section of the manufacturing process. Okay. Today we're going to look a little bit at this thermal section here. So we're basically going to take our material in the pellet form or whatever, or powder form, whatever it happens to be. We're going to compound it, mix it. That's got to be it. Mix it with whatever we need to mix it with, and then we're going to heat it up, and we're going to go from a solid to a melt, or at least something that will flow. We then process the material by flowing it through some kind of shaping device. Now, whether that's in injection molding and micromoulding, that's 3 now. All right. Whether that is in injection molding, where the form is created by the mold, or whether it's an extrusion where the form is created by the die. Okay. We then want to cool that down here, okay, to go from melt or nominally melt down to solid before gaining our end product. Okay. So it's all about controlling these things. So you have really a thermodynamic process here and a thermodynamic process there. In between, you've got this flow process. Okay. It's as simple as that. And that is the same whether it's for extrusion, injection molding, blow molding, where we make bottles, etc. All right, or micromolding, exactly the same stuff. So just looking at crystallinity, okay, so this is a blown film bubble, right? So this is used for making plastic bags, okay, this process. I don't think you've been introduced to it, have you? Nope. Okay, so if you want to make a bag, all right, then obviously it's no good just, you don't print a flat sheet, another flat sheet, and then stick them together, okay? Instead what you do is you extrude, and then you extrude into a bubble, okay? Into a ring, an annulus, and then you blow air up the inside, okay? So this is the extruder here, okay? Air is being blown up the inside, so you can form this bubble. Now, this is a fairly small one. In industry, these can be 20 meters high. So in particular, the ones north of here in Wigton and in China, they blow bubbles that are about 20 meters in length, and they have whole buildings where the bubble is there. So you can imagine if they mess it up and the bubble meets, you can imagine the cleanup that needs doing and to reset the process, etc. Because what they're trying to do is to keep a continuous process the whole time. This is indeed in the UK now. We have plastic £5 notes, okay, which you may or may not have seen. Okay, they're produced using exactly this process up in about 100 miles north, and just past where you're going today, actually. So what you can see here, you've got a melt, and then at some point the material starts to crystallize. Okay, so we go from this clear structure, transparent structure, to a white structure on this line, roughly speaking on a single line. We can do analysis on that to see what's happening. So what's actually happening with the crystallization? What we're doing is we're cooling from maybe, I don't know, 200 degrees at the die down to something that hits the crystallization temperature or the recrystallization temperature of the material. Okay. In this case, this will be polyethylene, so that will be coming in somewhere around 120 degrees. Okay, that's when these things start to form. So how do we understand that? Now, before we start looking at crystallinity, we need to make sure, this is just really good experimental practice, we need to make sure that if we're going to heat things up and cool them down, that we're not ending up with a different material at the end of heating than we started with, okay? So there's two thermal techniques involved. This is known as thermogravimetric analysis, okay? And you'll be seeing this in the thermal analysis section upstairs, okay? It's pretty simple, all right, but it requires real accuracy. So all we do is we take a small amount of material, like milligrams, 10 milligram, 20 milligram, okay, and we put it in a pan. That pan is weighed with the material in, and then we heat it up. As we heat it up, then the material starts to degrade. When it starts to degrade, it burns off, and so your mass starts to reduce, okay, so that you can see what your degradation temperature is going to be. If you test anything or process anything beyond your degradation temperature, then you are in a world of hell, basically. Nothing is going to pan out for you, okay? You'll lose all your structural integrity very easily. So all we do is we put a small sample into a pan and heat it up in a very accurate furnace, typically under nitrogen, so we don't set everything on fire. And here we can understand, as I say, degradation temperatures of material, but you can also understand moisture content. So some polymeric materials, nylons, polyethylene terephthalates, PETs, and other materials are very hydrophilic, okay? So they will take moisture in from the atmosphere and hold it within the polymer itself. And this can cause real processing problems, because basically what you get is when you start processing a wet material or a slightly damp material, for instance, nylon may take on 2% of water. As soon as you go through that transition at 100 and all the water starts steaming off, then you can imagine what you get in your polymer, in your nice, steady, controlled process for hundreds of thousands of pounds, is you get bubbles of steam blowing out, okay? And you'll never get a good product out of that, okay? So some materials you've got to be very careful to dry, but you need to understand how much moisture they're likely to take in the first place. And simply by looking at the transition around 100 degrees, you can actually get a measurement of the moisture within your samples. So here's just an example of typical traces. So this one we were using polyethylene terephthalate, okay, so the stuff we make plastic bottles out of, to produce nanocomposites. So we were adding clay into our material, okay? So tiny nanoparticles of clay, or nano on the in the gallery size anyway, and we were trying to choose which ones we should go for, okay? We need to know which clays are going to degrade, which clays aren't going to degrade at the temperatures at which we process PET, which is roughly around 260 to 280 degrees C, okay? And these are the results. So here we've got 1, 2, 3, 4, 5, 6 different clays, and this is our process window for the PET, okay? So everything starts pretty much at 100%, as you would hope it does if you calibrate it exactly right. And simply by increasing the temperature at a certain rate, then you start to see the weight drop off, okay? And that means your material is degrading massively and starting to fundamentally burn, but under nitrogen, so not burn, but just degrade. So we were trying to pick the right clays to start using in this section. And you see nothing is fantastic. By the time you get into the processing window here, we've lost about, I don't know, 8% of our clay mass, okay? One of the ones we were originally going to look at was this 10A, this particular form of clay, Montmorillonite, where you've lost 20% of your mass by the time you get to your process temperature. So we decided, right, okay, we will not use anything in there, but we will focus in on these three that are held within here, okay? So that's what TGA gives you. The other thing it can give you, if you have a composite of two different materials, and I was chatting with a young chap over there yesterday, he's going to be putting metals into polymer, okay? When you compound metals and polymer, or you compound two polymers together, you need to know how much you've got back out. What is, you know, you say you've got 50%, 50%, chances are you haven't got 50%, 50%, okay? The only way you can measure it is through using TGA, okay? You will see the different transitions for the different materials and you'll be able to pick them out very easily, okay? Once you've got your degradation temperature, you can move on to the DSC, which is the differential scanning calorimeter, okay? Now this tells us a lot about our material. There's fundamentally, nominally, 3 transitions for a semi-crystalline material, okay? There's a melt temperature, there's a glass temperature, TG, and there's a recrystallization temperature. I'd like to say that's the end of the story. It's actually slightly more complex than that, and we'll see that just now. These materials, the bulk of commodity materials, so your polyolefins, your polypropylenes, your polyethylenes, etc., and nylons, and probably 70% of the world's polymers that are produced are semi-crystalline. And what that means is you have crystals, when in the solid phase, in an amorphous matrix, okay? So there's a percentage of crystals and there's a percentage of non-crystalline material, okay? We can control that to a certain extent through processing, but even then, we can't control the crystal form very easily. So have we got any chemists here? Good, I can say whatever I like and I might get away with it. Okay, I'm no chemist either, okay? Crystals can take more than one form, okay? So a crystal of water, for instance, in ice form, can have quite a lot of different crystal forms depending on what's happened to it prior to it forming, okay? And polymers are the same. They exhibit what's called polymorphism, okay? So a material I'm using next door, PVDF, it's a semi-crystalline material, that has 4 different crystal forms depending on how you form it, okay? So you end up with these polymorphs. Now, some of these crystals will be very strong, and generally, thermodynamically, that's what the material wants to produce. However, it's not always the case. By putting process history, by heating, cooling at different rates, by putting flow in, you can change the crystal form. And so you may end up with lots of crystals, but they might be very, very weak. You can end up with twisted crystals, which are phenomenally weak, okay? And will give you wear problems and give you impact strength problems and all sorts of things, okay? Despite the fact your crystallinity still looks quite high, okay? So it's not enough to just say, right, high crystallinity means strong part, basically. That's not always the case. So some materials are simply amorphous, okay? So polystyrene, perspex, or PMMA, polymethyl methacrylate, or acrylic, as it's known, or lucite, as it's known. These are amorphous. They do not have crystals within them, okay? So you can go searching for a melt point as much as you like, you will never find one, okay? The material doesn't melt, it just becomes soft enough to allow it to flow, okay? So that's the key difference between them. So in order to understand this, we take a very small amount of material and we put it in our differential scanning calorimeter. And again, all it does is heat and cool the material, this very small amount of material, at a known rate, and from that we can measure thermal transitions. How does that work? Okay, so this is the one you'll be using today. It's a Discovery DSC. It looks quite fancy. It's not particularly fancy. All the working bits are that bit there, okay? This bit's add-ons. It looks very nice. It's got robots moving around and stuff, okay? But actually, the work is simply these two little nubs in there, okay? And this is what it does. You put your sample in a sealed metallic pan, okay? Generally, aluminium is absolutely fine. We need to know the mass of that. We need to know the mass of the sample. And we compare the thermal history of that, the enthalpy that's in the material, or that we're measuring, with that of an empty reference pan, okay? So we've got a reference pan on one side and a sample pan here, okay? And what it allows you to do is to see this, okay? So this is a typical trace. This is for nylon 66. This is when I was working for a company trying to figure out why their nylon products, which are in deep mines in Siberia and Australia, why they keep wearing out, okay? And they were to make tracks to take water and electricity to the coal seam in these mines, okay? You're 2 miles underground, okay? And these things run for about 2 miles or 2.5 kilometers underground as well, okay? So it's not quite as easy to say, well, this one's not working, we'll just get another one. This is kind of 2 miles, 3 kilometers, say, of chain links, which all need to be replaced in an abrasive atmosphere with lots of coal dust everywhere, wearing everything down, okay? You can appreciate why it's necessary for them to increase the wear of their material as much as possible. But this is what it shows. So all we're doing is we're heating the material, see nothing, 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 and then suddenly at around 220 degrees C, you get this peak. So where does this peak come from, okay? It's associated with the melting of the material, but why can we see that in terms of the heat flow going into our material? The reason we can see it is due to the concept of latent heat. Have we come across latent heat before? So you have a heat of fusion and a heat of crystallization, which is either additional energy required to form bonds or to take away bonds, okay? So with water, if you heat it up to 0 degrees, okay, it doesn't melt straight away. It takes extra time in order to, and extra energy in order to break the crystal bonds, okay? So it's what's called an endothermic peak. And that's what this measures here, okay? So all we've done is we've gone through the melt. Here we're fully molten. We've got a molten polymer. And then we drop it back round with the temperature, you know, and you're in charge of setting your temperatures. You don't want to go anywhere near your degradation temperature or you're just going to mess up your results anyway. And then on the way back down, this is at a 10 degrees C per minute cooling rate. We're getting a recrystallization peak at about 190, 188 degrees C, okay? Looks quite easy, looks quite nice. It's all right, it's all right. For nylon, it's okay. So heat, melt temperature, cool, crystallization temperature. Now the other thing you can get out of this, okay, your enthalpy here in the endothermic part, in the melting, if you've got a huge number of crystals, then the area under this curve will substantially rise, okay? And the area under this curve allows you at least to get the enthalpy out. If you know what the heat of the, if you know the enthalpy of a 100% pure crystal, you can work out a percentage of crystallinity of your part, okay? Now I don't like that very much, okay, because of the fact you get different crystal forms. And different crystal forms give you different enthalpies, 100% enthalpies, okay? So when people divide by this to give you a percentage crystallinity, looks great on paper. However, what you're actually doing is you're taking your measurement, which is pure and good and nice and nothing to do with the observer, and you're dividing it by a number that you know may well be wrong. Okay? Now, why would you ever do that? Why would you ever make your results less accurate than your results? You know what I mean? So it's something to be careful about. You'll see more complex pictures. So here are some standard polyolefins, okay, an HDPE, an LDPE, an LLDPE, and a PP. So low density, linear low, high density, polypropylene. Okay, so I'll just work out which way I'm going. These graphs can go either way. The negative is sometimes above and the positive is sometimes below. Chemists always do it the other way around. Engineers tend to do it this way. So our polypropylene is melting about 160 degrees C. Our HDPE at about 125 degrees C. Our LLDPE is about 115 and our LDPE is about 105. Okay. Now if we just look at this LLDPE, you'll see an example of what I've just mentioned basically. This kink on the side of this nice Gaussian curve, all right, which describes our crystal, it's got this extra kink in, okay? That is associated with a second crystal form, okay? Now the difficulty with the second crystal form is we can't really tell from doing a standard DSC what that crystal form is, and we can't tell how much of it there is. But we know it melts at roughly 110 degrees, whereas the other crystal melts at maybe 115, 120. Right, so what's actually happening during our test is we're heating the material, we get to this point, and we melt, say, crystal beta, okay? Crystal beta is now molten, and some of crystal beta will then form crystal alpha, okay? And then we'll keep heating, and then all of crystal alpha will melt at this higher temperature, okay? So this peak, you can't simply subtract that off and suggest that all of that is the original crystal form. We've actually changed the material by doing our test, okay? So it's something we need to be pretty careful about. Heat, cool, melt temperatures, etc., crystallization temperatures, okay? Now for an amorphous material, this is what the thermograms look like, okay? We've got a polystyrene and an acrylic, okay? No melting peak anywhere, okay, because there are no crystals within there, okay? So you can't take that. But what you can get is a different transition, and this is known as the glass transition temperature, okay? So if you think of polystyrene, you know, polystyrene rulers or acrylic rulers and stuff, they're pretty glassy, okay? They're not very flexible. They're kind of like a glass. If you hit them with a hammer, they will smash, okay? They'll splinter. If you hit polyolefins with a hammer, they won't. They'll just absorb energy, okay? Unless you go to about minus 50 degrees C, in which case they go through this transition similarly, and they will become glasses, okay? So this is also capable of measuring this glass transition temperature. Now the DSC, this is done on our older DSC, which can only go from ambient up, basically ambient temperatures up. The one that you'll be using today will go down to minus 90 degrees C, and if you attach liquid nitrogen, you can get down to about minus 150 or so. So we can start to look at the glass transition temperatures of these materials, and you can shift that up and down using subtle chemistries and a variety of compounds. But anyway, this glass transition always looks like a sigmoid, basically. It's, I'd say the blue one's a bit difficult, but if you look at the red one, then you've got a sigmoidal S-shaped curve, okay? And that's what the glass transition always appears as. Sometimes it's very small, and you need to really zoom in order to find it, okay, on your graph. Anyway, okay, that's what the amorphous ones look like, and I keep doing that, okay. Is that complicated enough? Should we make it more complicated? Yes, let's, okay? So this is polyethylene terephthalate. When we heat the material, okay, so the red is the heat, we get this glass transition, okay, at roughly 55 degrees or so. And we heat the material up until we get to about 120. And then all of a sudden we've got this exotherm. Okay, so here's our melting endotherm is over here. And yet here we've got an exotherm. So what's occurring there? What can be happening with our material that's actually the opposite of melting? What's happening is the material is starting to cold crystallize, okay? It's starting to form additional crystals at this temperature. And this is complex in terms of DSC, but it's fantastic for recycling, okay? This is why this bottle is made out of probably 99% recycled PET, okay? Because it's a living material. You can regrow its strength, okay? So there's a question yesterday, I can't remember who from it, was talking about recycles. If you send this stuff around a recycle route lots and lots of times, then you gradually make your material weaker and weaker. The great thing with PET, a material similar to it, PLA for instance, all right, is that it doesn't matter. You can regrow it by holding it at this temperature. Okay, it's a thing known as solid state polymerization, SSP, okay, and it means that your bottle is as good as new just by holding it at that temperature before you start processing it, okay. So you just heat it in an oven, it all comes back to form, okay. So we have that complication, and we've got to melt, and then we come around recrystallize. So what we've done in this case as well is to heat it up again, and you'll see when we heat it up again, we don't end up with a recrystallization, this solid state recrystallization, but what we end up with is a double peak on the top of this temperature curve here, okay? Again, associated with two different crystal forms appearing, okay, within our material. So these are single materials. A lot of materials we use are blends. So you can imagine how these curves get pretty bad pretty quickly. When you look, this is the materials I showed the rheology on yesterday, sorry, it's been a long week. All right, okay, these are these vinyl acetate copolymers. Basically they're polyethylene with a vinyl acetate comonomer in them, okay, polymerized together at different percentages. Okay, as I say, this one, the low one at 2% VA, is used for greenhouses and for growing plants, etc. It's the plastic sheeting. It's got a bit of stretch to it, but not very much. By the time you get up here, you're looking at a hot melt adhesive. So the thing, when you buy a magazine that's got a CD on the cover or whatever, if people still do this, I don't know, a cassette, all right, okay, you'll find this glue on the back. That is this 38.7 vinyl acetate, okay? In between are, as I say, the gels in trainers and stuff for runners. Okay, so this vinyl acetate content, what you can see is here's our melting points. This is the lowest vinyl acetate, and slightly up, slightly up, slightly up, slightly up, slightly up, okay? So basically by adding more vinyl acetate, we change the crystallization temperature massively. Why is that important in terms of process? It means that we don't need to put as much energy into our process to get it to work, okay? We can, with this material here, we can process that material at about 90 degrees C. With this material here, we can process at about 130, 140 degrees C. So the energy we require to put into our process, which can be huge, all right, we can reduce massively as well. And this is one of the big advantages of polymers in the first place. This is why this bottle is no longer made of glass. It's now made of plastic because it processes at about 280, whereas glass processes up at, 700, 800 degrees C, yeah? So the energy usage is massive. And I keep showing that, okay, but that's okay. So just taking those results out, then you can see your melting temperatures and how they scan with the vinyl acetate content, and similarly your crystallization temperatures as well. Now I would have done the actual crystallinity, but the story gets quite complicated down here. Up here we've got single peaks, down here we've got kind of wavy peaks. There's all sorts of different crystals occurring down there, and so I can't simply divide through to work out a true crystallinity value. So we have to go to other techniques. So just one more example. Well, I've kind of shown that anyway. This is just looking at these nanocomposite pellets again in PET. So we've got this solid state polymerization prior to our melt. And this is really, if you look in the detail and start to look at these curves, you'll see that the curves occur at different points. Okay, so by adding these nanocomposites into our material, these clays, we can change the melting point. Okay, but what you'll also see is a spread in the curve. Okay, now that spread in the curve tells us something about the crystallization kinetics, how fast these crystals are forming. Okay, so we can put lots of, these are all done at exactly the same rate at about 10 degrees C per min, but you can see by changing that, you'll be able to change the crystallization kinetics, how fast this material will crystallize. Now in micromoulding, you can pull out, I think it's 10 to the 6 Kelvin per second, okay, because you're looking at a very, very small part. You've got Peltier cooling, okay, so you can rip temperature out very quickly. But sometimes that's not always the best idea, okay? Reduction of cycle time isn't necessarily the gold standard that we need to achieve. If we want a part that's truly got the properties that we want it to have, then maybe we don't just need to make it as fast as we possibly can. Though I understand that is the big push from all manufacturers, is to do that. But if you end up with lots of rubbish parts within 24 hours, that's not as good as 5 really good parts within the same amount of time. Okay, and just doing some extra analysis on this, we can look at the crystallization half time by adding 1% up to 20% of these clays, and you can see we can dramatically reduce the crystallization half time. So we can form these crystals a lot quicker. And the reason they form a lot quicker is similar to bubbles in the bottom of a champagne glass or bubbles in a Coca-Cola, okay? They nucleate, okay? And they nucleate on surfaces, these crystals. If you've added in fundamentally dust in the form of clay, okay, then your crystals will nucleate on the surface of these clays, okay? And so that's why we can get much better crystallization profiles than we could otherwise. And this translates directly into our solid properties, okay? So this is our crystals forming, how fast they go, and these are the tensile moduli that we're capable of getting back out by doing testing under uniaxial extension, okay? All right, I won't go into those. Okay, so we've got crystals. Well, what are they, okay? They're real things. We need to understand them slightly more, okay? So here's a slide I nicked off a colleague some time ago, okay? There's a whole range of different orders of magnitude within here in terms of the size of these crystals. We start off with the basic crystal lattice, which is at an order of about 1 angstrom, okay, or about 0.1 nanometer. These lattices then fold and they form into these other structures at an order of a much greater, about 100 angstrom or 10 nanometers. We then have fibrils, we have fibrillar branching, and we have our friend the spherulite, okay? So traditionally when you see polymer crystals, that is what you will see is an image of that, okay? Which is basically a fluffy sphere, okay, with all these tendrils shooting off. The nucleation point is right in the center, and then these crystals will grow and grow and grow. Now we can control their growth, and we can control how big they get to. We can control how many of them there are through understanding our process. The other thing we haven't covered is how does the actual architecture of the molecule, okay? So each molecule has a kind of topology, a map of itself. How does that affect crystallization, and what else can we do? So here's a couple of recent results from one of my PhD students looking at spherulites growing. This is a polyethylene oxide, which you find in hair gels, you find it in pharmaceutical medications, you find it in a variety of different places, known as PEO or PEG, polyethylene glycol. So basically, if you look in your bathroom at home, you will find there's about 90 polymers within your bathroom, okay, just in the products that are dotted around, okay. PEO and PEG take up quite a lot of that range, basically. So we are, you shampoo your hair, you're basically putting polymer all over your hair. That's what you're doing, okay? Makes it shiny and lustrous, and because you're worth it, this is what you're actually doing, okay? So this is the growth. So this bar here, which you can just about read, is 100 micron, 0.1 of a millimeter. These spherulites have grown from nucleation points, okay, under cooling. So we're cooling the material down, a thin film, looking at it under a microscope. It nucleates, and then it starts to grow. Now, what we're interested in is how we can control that, okay? But they will continue to grow until they meet another crystal, okay? And so you can see this boundary that forms between the spherulites. They're basically growing until they can grow no more because they've met another crystal, okay? Looking at a slightly different cooling rate, you can see we're now getting a range of different crystal sizes within this material. So each spherulite, again, has these nucleation points. You've got big ones down here, very, very small ones in there. So you're not going to get one size of crystal, you're going to get a whole range of size of crystals. Now, in moulding, you've got lots of things going on, okay? You have, if you look at your micromoulding process, all your temperature is controlled at the wall, okay? There's nothing controlling the air gap in the middle, okay? So you can see that the thermodynamics of what happens in the center of a mold compared to the thermodynamics of what happens at the wall of the mold are entirely different. If you look at your flow, and I'll come on to flow very briefly and how rheology impacts on this. If you look at your flow, then your shear rates are greatest at the wall, okay, because of the no-slip boundary condition. Like the velocity of the material nominally needs to be 0 on the wall. If you take your part and section it, this is what you see, okay? So these are simply under cross polars. It's by a guy from Austria, Jan Schütz-Kriegel, one of the best people on crystallization. And this is produced here, I believe, okay? You can see a wall region and you can see a central region. And the same in this part as well, okay? The crystal form at the wall is entirely different to the crystal form in the center. In the center, we're broadly getting these spherulites, okay? But on the edge, we're not. We're getting a different type of structure entirely. Now, whether that is a good thing or a bad thing, it depends. It depends on what you're trying to do. So all crystallization, flow-induced crystallization, it's a relatively novel field, relatively new field. This interaction between crystallinity, temperature, and flow is relatively unstudied. There's some groups looking at it, and we're one of them. And so everything has strange names, okay? So in the center, we have spherulites, large ones right in the center where things have got time to grow, smaller ones next to them, and then out here in the wall region, we have what are known as shish kebab structures, okay? I'm not in charge of the naming. I've got a colleague in Nebraska who's also observed sausages along these dotted lines as well, okay? So get used to it, because no one can come up with a better name, all right? So we have sausages, and the sausages go in different aspect ratios depending on where you are in this region. But if you look at the spherulite, okay, you've got a everything is growing in every direction equally, pretty much, okay? That's how we get a sphere. If you look at the shish kebab out here, it's a different type of structure. You actually have structures along the flow direction and structures orthogonal to that, at 90 degrees to that, okay? So one is the shish, the other is the kebab. I still don't get it, all right, but this is what it does. And so you always end up with this characteristic multi-layered part, okay, which is very, very complex. Now, if you want a part that wears very well, okay, that's one of the key things it needs to do, is to be able to be under a wear situation for years, then you want a high level of crystallinity at the wall, and you want a high level of very strong crystallinity at the wall. Your crystals need to be the right crystals to withstand being gouged the whole time, okay? So we begin to try and understand exactly what's going on in here. And the way that we can do it is using a different method. And And this is X-ray scattering, which you may have come across before. This is the kit that we use upstairs. This is going to be very brief, this part. Okay. We have a benchtop X-ray kit here, and it's fine for understanding crystal forms. Okay. It's not fine for understanding how crystals actually form, because it's the size of this. Okay. If we want to understand how crystals form, we need to use other techniques, and I'll show you how we do that. But this is the one we'll play on today for a little bit. So we have an X-ray generator, we have a camera, and we bounce X-rays directly through our sample. Okay. We end up with scattering diagrams something like this. Okay. Each ring is associated with a length scale within our material. Okay. It's associated with a crystal form within our material. That's simply a silver bayonet, so it's a very nice scatterer, so I know exactly what it's doing. Now the whole thing relies upon, well, the whole purpose of using X-rays rather than normal light is that normal light we can get down to about 400 nanometers. That's our diffraction limit. Okay, that's in the UV. Okay, if we want to look at things that are smaller than 400 nanometers, then it doesn't matter how many lenses you put on it. Okay, there are ways that get around this, like TEM and SEM, but it doesn't matter how many lenses you put on it, you can never go beyond this diffraction limit. X-rays have a very small wavelength. Okay, the one we use is about 1.54 angstrom, which means we can get our scales right down. Okay, we can start looking at tiny, tiny things indeed, okay, which is the whole purpose, because these things are very, very small. Our X-ray allows us to get to about 0.13 nanometers, so about 1.3 angstrom, okay. We can get some level of detail back out if we're careful. And it all works on this beautifully simple law known as Bragg's law. Like all good laws, it's not complex. It's very simple and easy to state, okay? And all it says is that the scattering angle, so if we assume this is at 0 degrees, this will be an angle generally known as 2 theta of a certain number of degrees, that another, that another, that another, that another, okay? The scattering angle is related to the wavelength of light and a length scale, D in this case, okay? Now you don't just see the crystals, you can see how crystals stack. You can see how clays align. You can use this technique for a huge range of different length scale determination. And this is all it does. You have an X-ray source here. You put your sample in an evacuated chamber, and you have a camera on this end, okay? That's pretty much it. Fire it through. X-rays scatter off the crystal, off the faces of the crystals at certain angles, and from that we can infer quite a lot about our material. Similarly, if you have particulates within there, they will scatter off associated with the distance between these particulates. Okay. There's a lot of analysis further down the line, but it works kind of well. Now, the good thing with this kit, and the good thing with good X-rays, is you can use small angle and wide angle. So you can move your sample you can change your sample to detector distance. Okay, and by changing your sample to detector distance, you can extend the range of angles over which you can see. So when you see X-ray patterns, everything is in reciprocal space, okay? So the thing that looks the furthest away, just looking at this image, out here, the structures out here are the small structures, okay? Takes a bit of getting used to, all right? Here are our large structures, okay? These are in sort of around 10 nanometers. Out here, you're looking in the angstrom range, okay? So you need to twist your thinking to be reciprocal space to understand scattering. But it's fairly simple. And here's some very brief results. When I was doing the rheology yesterday, I showed you some, I tried to show you a geometry, but it was jammed with this gel, okay, which is this copolymer. Okay, do you remember that? I tried to twist the thing, but it was all jammed. That was Banner's fault, okay, at the back. Because Banner is working on these hydrogels for drug delivery, okay? So what we've done here, we've added a small amount of a polymer, which is a tri-block copolymer. It's basically polyethylene oxide, polypropylene oxide, polyethylene oxide, then polymerized. We've added certain quantities of that at 0.1 to 30. Okay. And when we look at the scattering patterns, okay, if we go from 0.1 to 1 to 5, 10, 15, 20, you can start to see structure develop, okay? And these structures have massive influence on our viscosity of our materials, and likewise the other way around, vice versa as well, okay? And we can play around with these structures quite a lot by adding extra things in. Okay, so here we've added some extra additives, an additional PEG. We've added some other polymers in there in different weights to see what we can do about this crystal structure, how we can control the crystal structure to give us what we want, which is drug release. And that's nice, it's good. But what actually influences crystallinity in the final part, okay? If you go away with nothing else from this lecture, then this is the key, all right? What influences our crystallinity are all of these devices, all of these things here, okay? We've got the chemical parameters to do with the molecule themselves, the architecture, the molecular weight distribution. You can blend polymers of different molecular weights to give you entirely different features. Even at, say, by putting 1% of a high molecular weight into a 99% of a low molecular weight, the 1% dominates your crystallinity, okay? And you can play around with these things as much as you like. There's huge areas of space to do research in to get the ideal thing. So once we've got our material, then what can we do? We can control crystallinity through temperature, through the melt temperature. We can control crystallinity through our mold temperature in a molding. We control through how we cool that material straight after injecting. We can control crystallinity by injection speed, i.e. the rheology of the material, okay, because that's the flow and the resistance to flow, and also by geometrical parameters, by milling, by FIB, by whatever, to make whatever part we want, okay. We can change our shear rates, our extension rates. We can change the depth. We can make it a more 2D part or a 3D part. We will all infer different crystallinity in our final sample. And this is the effect of shear, okay? This is using the same gel, okay? This one is unsheared. This one is sheared. Sorry, I should have actually written that on, okay? It's exactly the same material, and you see entirely different structures, okay? What we're actually looking at here is micelles, which form at about 10 nanometer diameter, okay? But they form in certain ways with the crystals that are nearby as well, okay? Now the problem with this is each one takes at least 10 minutes to get a decent picture, okay? So if you want to look at the kinetics of formation, how these crystals go about forming, that's no longer, it's not viable basically, because these things will form over, you know, seconds, milliseconds in the micromoulding process. So how might we go about investigating those? We need to use big tools, okay? And here's three that I use, which is ESRF in Grenoble, okay? This is Diamond down near Oxford in the UK, and this is just a schematic of the one in Brookhaven in the States that I also use, okay? These are basically massive microscopes, okay? The X-rays in here are 1 billion times brighter than those you get in dentists, okay? So when you get your teeth done, they're X-rays, but they're real X-rays, okay? They're 1 billion times brighter. By having this massive intensity, focused intensity of X-rays, then you can get a frame out at about 1 millisecond, okay? So you can get your X-ray image, you can be cooling, you can be shearing, you can be doing all sorts. And you'll see that has a real effect on the crystallinity itself. So we use special tools. This is a shear cell. So it's basically a mini rheometer, okay, that we mount into our beamline, okay, so where the X-rays are going through. The cameras here are 8 meters in length, okay, fully evacuated tubes and massive, okay. so we can get everything out that we need to get out. An example here is we actually took an extruder, we mounted it in the beam line, so the beam is going through there, the x-rays are going through there. We hauled off the material at a very gradual rate, but a controlled rate, so we knew exactly what the force was. And this is the type of thing we saw. So, when I showed you the round scattering pattern, what that is an isotropic scattering pattern. That means that everything is scattering equally around every direction, i.e. you have no orientation within your material. Now, if you think about die drawing that you've seen, and you think about hauling material through, you're orienting the molecules, okay, and in flows as well. Okay, as I said yesterday, you start to stretch these materials, and that's why they start to shear thin and the viscosity curves. So you're actually orienting your materials. So instead of getting a nice isotropic scattering pattern, in fact we don't. We see nothing out here. These are just at different haul-off rates. Okay, all of your orientation is in the draw direction. And that infers, again, quite a massive change. I'm ambitiously going to play a video. And this is what happens, okay? So this is tracking that haul off at 0.001 seconds. And what you see is this main oriented structure, but you can also see a structure going the other direction. So this is one of the first observations of that shish kebab structure actually forming, okay? So the fact you've got these orthogonal crystallization directions occurring, you can actually see it using these techniques, okay? And then you can begin to study how they form and why they form. And one way we did it was taking an injection molder and putting it into the system. We took 800 kilograms basically of kit and put it into the beam line, heated the material up within here, and injection molded it into this very small region here and put the X-ray through it, okay? So this is our pressure pulse. We've got this massive pressure pulse. So basically we're flowing the material at the same time as crystallizing it. And this is a typical effect. This is a quiescent crystallization. If you just leave it there and leave it to crystallize at a temperature where the material will crystallize, near the crystallization point, maybe 1 degree below, after an hour, nothing has happened. The material will crystallize eventually, but in this material in particular, it took 3 days, okay? Very, very slow. By putting a pulse of energy into our material, i.e. flowing our material, this is our crystallization profile, okay? Everything is done within a third of the time. So you can think about playing with your temperatures, playing with your flows, playing with your injection speeds to give you the crystallization profile that you actually want. I'm feeling that's not going to do anything. Oh no, okay. So this is the quiescent isotropic scattering pattern, and this is what you get with shear. What else can it give us? As we've said, it can also give us this orientation measurement, okay? So we see it in injection molding parts, particularly if we inject them fast and we cool them rapidly. We don't, okay, one of the limitations of our machine upstairs is the camera is not massive, okay? All right. The orientation, because of the nature of scattering, if you can see 90 degrees of your image, then you've got it. So a quadrant of your image, then you've got every measurement that you can get out. The rest are simply repeats, okay? So just going back. So basically you don't need all of that image because the top and the bottom are mirrored and the side are mirrored. So actually to get a full measurement out, you just need 1 quadrant of your results, okay? Now I say this because we're cheap. All right, our cameras are £150,000 or 200,000 euro. Well, no, 150,000 euro now. All right. If you buy a full detector, That's 500,000 euro, okay? That's a lot of money, so we didn't have that. So, but what you can see is just by getting 90 degrees, then you can get an image out. Okay, right. There's different techniques for looking at this, for measuring orientation, and this is where they all are, and you'll have these in the slides. They work in different ways, and they work for different things. Some work for amorphous materials, some work for crystalline, some work for crystalline and amorphous, and some have all the accuracy in the world. Wide-angle X-ray and small-angle X-ray, brilliant for crystalline materials, rubbish for amorphous materials. They simply can't see any amorphous material because there's no crystal for them to scatter off. So for that, we have to use neutron scattering, which I'm not going to go into today. But anyway, you'll have that. Just an example in terms of, not the best example in the world, in terms of micromolded samples, this is something I did years ago. Looking at the different regions of these plaques, okay, so look at 9 and 10 in here, you get different orientation in different parts of your part, okay, different locations within your part. So these were only suck it and see measurements. This is your unoriented polyethylene, okay, nice rings, everything, we know what it all is. And this is what you actually see within a micromolded part. Now, depending on where you pick, you will see different things. So the resolution at which you can measure these things becomes very important. Just going to conclude. Crystallinity confers a wide range of final product properties, okay? Obviously, in semi-crystalline and crystalline materials. Strength, impact, opacity, all related to the quantity of crystals, the type of crystals within there. You can get measurements of bulk crystallinity using the thermal techniques you'll go on to look at very soon, okay? All of these things influence the final crystallinity of our material, and using other techniques like X-ray, like neutrons, like a variety of more complex techniques, you can start to determine the crystallization kinetics and thus tune the crystals to be what you want them to be. That's all, I think. Oh yes, I've just put that up. That's your take-home thing, please. That's your key, all right? That's your play area, okay? You can do anything within that to give you the part that you want. Thank you. Any questions? Cheers.
Yeah. Well, in cases of like in the TGA,
Yeah.
not TGA, sorry, DC, when you have like two peaks,
Yes.
very close or different polymorphs.
Yeah.
In some cases, you can like change the heat transfer, like make it slow, and then you have like can see this.
Yes.
Separately, these two peaks.
Absolutely. You will separate them slightly, but you're still within a limit of operation of your DSC. Okay. If you go much lower than 0.5 degrees C per minute, okay, you won't. You just end up with noise, basically. Okay. So you can separate them a bit by reducing your cooling rate, like your heating rate. But the other thing you can do, you can use a technique called modulated DSC. Okay. So instead of having a linear ramp, you actually put a linear on, and then you oscillate above and below.
Okay.
Okay. It's called modulated DSC. And what that allows you to do is see whether any change is reversible or irreversible. Okay. So basically, if you're heating a ramp, when you go through the first polymorph, say, it will melt, but then it's going to reform into the other crystal form, which will not melt again. Okay. So that will be an irreversible change. Okay. Whereas if you're on crystal A in the big peak, then basically if you go up and down over that peak, you will get a reversible change. So you can separate, but it's quite a subtle technique. And to get your amplitude of your oscillation and also the frequency of your oscillation compared to your main ramp is complex. But there's stuff out there to help out, but it doesn't always work.
Okay. And what are the pros and cons to have simultaneous DSC TGA, like to have equipment with both? I've seen many equipments like.
To do them simultaneously, I'm not sure how it would help. You can you can do it, but you can't drop it back round and look at recrystallization again. Yeah. So the great thing with DSC is you not only see the heat, you see the cool, and then you can heat again. So if you've got process history within your material, you can actually see that by taking it around twice. If you run TGA at the same time, by the time you get to your degradation temperatures, if you want to cool down again, then what are you going to see? You're going to see an entirely different material. You've burnt out a lot of the material that's there. So yes, on a single run, I can see how that would work. But if you want to actually look at the effect of process history and the cooling, then it's not going to happen.
Do you have heat system in your X-ray?
A what?
Do you have a heat system?
Yes,
in your
we
X-ray?
have heating, we have grazing instance, so we can look at surfaces. We bought every possible sample environment we bought, basically, so that we can look at all these things. Yes, sir.
One of the slides we see that if you cool plastics, they absorb, there is a potential to absorb water.
So I'm not sure I can play it, sorry.
And when you heating up a plastic, so
Yeah.
they will lose weight because of water inside them.
Yeah, you'll lose weight because of the water, yeah.
And when you are cooling them, they absorb water.
They will absorb water, not through cooling, they will absorb water at room temperature. That's the thing, they're hydrophilic, and so they just take in the moisture from the air. So unless you, generally with PETs and with nylons, they need to be dried prior to processing them. Polycarbonates, exactly the same. You need to dry them at a certain temperature. In the case of PET, you need to dry them not in that big peak crystallization regime where you're actually going to change your material, but you need to dry the water out. So over 100 degrees, and processors will give you all this information on how to process with their material. So the data sheet will give you that. But yeah, a lot of it is to drop out the moisture.
So when you're blow molding that bottle,
Yeah.
there is a dye, and inside it's air.
Yes.
So when you are cooling it, so it absorbs some water from the air inside it.
Yeah, but it takes time for water to get into polymer. It's not an instantaneous thing. You know, it's not like it's not that is currently saturated with water. Okay, if I heat that back up, okay, and then cool it, it'll take a day to get enough moisture in to be saturated to its maximum extent. Okay, so it's not like it's just going to carry on pulling more and more. Otherwise, it'd be rubbish as a bottle. So everything would just go like that.
But for PET is not a problem, but for like I think ABS or EVA, like when you go to process in the filler there, some they have the heating to keep like warm.
Yeah.
Otherwise it gets down, like they absorb the water and cannot process.
Yeah.
So it's case of materials.
Normally you will have nitrogen blowing continuously
Yeah, yeah.
when you
You'll have
process
to-
PET for microinjection molding.
You will have dry nitrogen
Yeah.
out at the top
That's what you
rather than there. But also, if you look in the main lab, you see all these orange units on top of the injection molding machines, and they're dryers basically.
Yeah.
They're dehumidifying dryers. Okay, so you'll put in very dry air, which we get from our compressor, and you'll have them at temperature, so that material is perfect for feeding through. You also, one of the key things you end up with a problem with materials like this, and with PBOH or EVA, all right, your EVA, not my EVA.
Yeah.
All right?
Yes.
I keep having to say that.
Yeah,
The
it
acetate
is.
and the alcohol are not the same. All right? Don't put this stuff inside your body. It's not going to help. Okay? One of the key things is they start to bridge. So if you look at the individual pellets, you're trying to force these pellets into a small hole. What happens if you've got moisture is they get a little bit sticky and they start to stick together until you end up doing what's called bridging. Okay? You end up bridging your material over the top. So nothing's going onto the screw. All right? It's just sat there. And it's a real pain, okay? It's really difficult to get around once that started occurring. You need to strip everything, you need to clean everything out, okay? And it's this horrible mass. So it's something you want to be careful about.
And the material, that material is PET.
This is PET, yeah.
PET.
Yeah.
And do you have an example of composites between PET and other polymers?
There are out there. I don't have any off the top of my head.
I want to know the heat flow behavior of the composite, because in some cases it releases some, when you are heating it up, it releases some heat,
Yes.
I think.
It really depends upon the composite itself, okay? So we're doing work with PLA upstairs for a company, but that has 4 different additional polymers in. And I didn't want to put a DSC trace with all of these things in. I'll show you later, all right? But it's truly horrible. I've got the student that has pulling out his hair, the whole thing. He thought it was complicated enough with 3. We've now moved to a 4 material mix, and the DSCs are just horrible. Some cold crystallize as well. So he's got about 10 peaks to analyse on a single curve, and to try and indicate the effect of, say, 5% loading versus 10% loading of one of the quaternary mixes. I think he's just going to disappear in a puff of smoke very soon. He's gone 17-dimensional, and he's just going to, we won't see him again.
And please correct me if I'm wrong. With the smaller wavelength,
Yes.
we can scan the wall better, I mean the wall of the material better, more
Yes.
precise.
Yes, absolutely, absolutely. You can get better resolution if you can focus the beam down. Okay, so that's the thing. So this is a point source, so you're not flooding it as you do in X-ray in the dentist or whatever. You don't just hit everything with X-rays. This is a point source, so you're collimating your optics and you're focusing your optics to be as small as possible. In this case, you're looking at micron, basically, around a micron. You won't get much lower than that, but the detail you get back by focusing at a micron is at a lot better resolution than the micron. See what I mean? There are other techniques, optical techniques, so you'll see the TEM upstairs, transmission electron microscopy, which operates using some slightly different rules, the Dupuy rules, okay, which allow you to get lower than the optical limit. So it's a direct observation, but it actually runs very similarly to X-rays. But instead of being in this reciprocal space, this scattering space, you're actually looking directly. And you can pick up stuff around the angstrom level for that as well. But the problem is, if your parts aren't going to be angstroms, all right? If they are, then you're going to lose them, all right, for a start. Okay, your parts are going to be bigger than that. So you actually need a kind of bulkier measurement than perhaps TEM can actually give you. Now, there's lots of PhDs that have been done on looking at nanocomposites, so putting carbon nanotubes or graphene into polymers to improve their properties, okay? And a lot of those PhDs are a student looking at TEM images at different parts within a sample. Within 3 years, you can probably scan 2 millimeters square, I would suggest, all right? And they will say these are representative samples for how all our graphene is dispersed within our sample. Okay, except they're never representative, are they? They're not statistically representative. And the typical TEM image you see in every paper you see on TEM is not typical, because if you were producing a paper of all your work for 3 years, would you choose a typical TEM, or would you choose your best image? Which one would you put in? Okay, so there can be a huge amount of work in looking at this very fine structure, but actually the fine structure might not be truly representative of your sample. And so there are other techniques, spectroscopic techniques, for looking at larger areas. But it's a matter of, having the catalogue of all these techniques, and then being able to decide what is going to work best for you. And that is always a play between the resolution and the area over which you need to scan. Okay? And you need to come up with something that's, it's like doing simulation work. If you do a full simulation of the flow around a jet, you can do it, but it'll take you 1 million years to solve it on the computer, all right? So is it worth doing? Probably. I'd suggest not. All right, so it's a matter of playing with these things to give you the optimum technique to look at your particular thing of study.
So what do you do when you want to look deep into your material?
There's a variety of different ways. It depends upon the material. We can use confocal Raman spectroscopy, use confocal fluorescence microscopy. We can, if you've got a three-dimensional gradient, you might want to section your material. That might actually give you the best answer. As long as when you're sectioning the material, you don't change your material by sectioning it. So I can't give you a direct answer on exactly what you'd use. We have a micro CT in there, which will give you a 3D scan of the inside of your material, but only to a resolution of about 1 micron. Any smaller components than that, you won't get away with that, because for that you are flooding everything with X-rays. So if you want to flood everything with X-rays and get that massive resolution, then you need a synchrotron light source with a very big evacuated chamber with your sample shoved in the middle of it, basically. So again, it's a matter of exactly what the problem is.
Team, I have a question.
Yes?
Could you please go back to the first slide of fax pattern?
Yep.
Yes. Yeah. So why the fax patterns give the isolated
The spots.
spots?
Okay. Yeah.
Yeah.
Anna,
Yeah.
why are the isolated spots there?
Yeah.
It correlates with the liquid crystal format that you've got in this matrix. So basically, the micelles arrange themselves. This is liquid crystal. It's not like a real crystal. So liquid crystal have different properties from isotropic real crystal. So basically here we have different shapes and different formats. In this, I'm still working on it, but actually we have got 2 phases. It's 2 random phases, hexagonal phase and cubic phase. It's all in terms of liquid crystals as well. So basically these are not real crystals.
Is it common in your system?
Pardon?
Is it a common phenomenon in your system?
Yeah.
Just in liquid crystals.
If you want to go really complicated, look at protein crystallography. Every time I work at one of these beamlines, I turn around and I've got these nice rings, maybe a bit oriented, but I understand it's polypropylene, I know where they're going to be. I turn around and someone has got basically a screen that looks like an old television, all right? It's got all these dots everywhere, and they're all very excited, saying, look, that spot has arrived. So when you start looking in the biological world, everything gets very much more complicated. And so I just turn away and ignore them, okay? That's my defense, all right? But you may be more interested in protein crystallography, but there's a huge amount of work in that. And these crystals that form, you know, in the biological world, these are said to be responsible for a variety of diseases, multiple sclerosis, for Alzheimer's, okay? And they form in similar ways under flows of blood and other fluids within the body, different temperatures, different contractions, different shear rates, extensions. So the whole thing isn't just limited to these simple materials that look relatively simple materials. These are complicated.
How big can be a monocrystal?
Oh, you can grow crystals this big, can't you? You can grow massive crystals. Look at the, if you wait long enough, at the right sort of...
And they're like, okay, the salts, and they're like for a polymer.
For polymer, you're looking at, you can get millimetres, certainly.
Right.
The problem is if you've got one growing, you don't grow one in isolation, there's probably another one growing quite nearby,
Then
then they'll coalesce at some stage. So, I can't give you, it depends upon how big your injection moulder is, I guess. But millimetres, certainly. Millimetres. And probably higher than that. But,
in these pictures, why do we have light blue areas in the lower percentage of hydrogen?
oh, this is, you've got to be a bit careful with pseudo colour, okay? It doesn't really mean anything. Basically, you've got a direct beam here, okay? So that is where most of your energy is. 99% of your energy is in that beam. We actually put a beam stop in here So this blue thing here is actually a beam stop, right? And what that stops happening is all your beam hitting your camera directly. The problem with that is it doesn't damage the detector anymore with CCDs, it's fine, except it kind of floods. You get this parasitic image on, like ghosting on your camera. Anyway, that's enough. I've gone on for quite long enough, I think. I feel I have anyway. And now we need to run some other sessions. So thank you very much. Well done. You get to go play this afternoon as well. Sounds all right. I'll write another lecture. It's fine. I'll just do
We get more money. They pay like,
You can pay back for
yeah.
how much you